Hello students, here is the part 2, the reveal of what is going on when we go through this little problem that I found on social media. Take a 3-digit number where all 3 digits are different and take their 6 permutations. In part 1, first video, we looked at the notion of permutations. We saw that it was connected with this process known as factorial, so that when you have a 3-digit number, the number of permutations of that 3-digit number is 3 factorial, 3 times 2 times 1, which is 6. These are all of the 6 permutations of the digits 4, 7, 9. The problem has us add those 6 permutations and then divide that sum by the sum of the digits in one of the permutations. Now I've shown just about all the work here. I didn't show the carried digits in the addition algorithm, but you should have gotten 4,440 when you added the 6 numbers, and then the sum of the digits in one of the permutations is 20, so we divide the sum by 20 and we get 222, as we did with the previous examples in the previous video. Now, this video is about understanding why. I'm going to also go through the other one I asked you to do, the 2, 8, 9 problem. It's going to work out very similarly to this one. And then finally, we're going to show that it works for any 3 different digits. That's what mathematics is really all about, is proving that things are true when they are, proving that things are true in general for all cases. That'll be our final, the final part of this video. But what I was hoping you would have realized about this problem and the next, if you look at each column, the ones, the tens, and the hundreds, you'll see each of the 3 digits twice. It's obvious the way I've done it. It's obvious over here in the hundreds place. You see 2 4s, 2 7s, 2 9s. You'll also see that in different order in the tens and the ones place. And this is because we're adding up the 6 permutations. It has to work out this way. Now the problem then has us divide the sum of the 6 permutations by the sum of the digits in one of them, which is 20, but each column has 2 of each digit, so that sum is 40. Each of these columns adds up to 40, and 40 divided by this 20 is 2. That's why you get 222 for the final result. Let me show in a little bit more detail what I just said. This column here, the ones column, the digits add up to 40. So what I'm doing here is, because of this special case, because each column has 2 4s, 2 7s, and 2 9s, I'm going to use that special, unusual situation to add these numbers differently. We have 40 ones. We also have 40 tens and 40 hundreds. So this is sort of an unusual expanded form of this sum here, 4,440. I'll get back to that in a moment. But we have 40 ones. We also have 40 tens, because the middle column adds up to 40. And over here we have 40 hundreds. Okay? So if we evaluate this expression here, 40 times 100 is 4,000, 40 times 10 is 400, and 40 times 1 is 40. You can see it right here, the 4,000, the 400, and the 40. Okay? And then part 2 of the problem asks us to divide this sum, and I did it over here using the standard form of 4,440. Now I'm going to divide, this here is also 4,440. I'm going to divide it by 20. Notice the fraction bar to indicate division. And this is something that comes up in higher levels of math and in algebra, high school math. Sometimes you have a fraction with a single term, in this case the number 20, a single term in the denominator, and then multiple terms in the numerator. 3 terms in the numerator here. What we need to do is to divide 20 into each of these 3 terms. That's how you can evaluate a fraction like this. And the reason I usually give for why we approach it this way, dividing the 20 into each of the 3 terms, is imagine that we had a fraction or an addition of 3 fractions that look like this: 40 over 100, 40 times 100 over 20, then plus 40 times 10 divided by 20, plus 40 times 1 divided by 20. Please convince yourself that if you had this bottom line down here, we have a common denominator of 20. We could add those 3 fractions to get a single fraction with 20 in the denominator, of course. Don't add the denominators ever. And then the numerator would be 40 times 100 plus 40 times 10 plus 40 times 1. Exactly what's up there. This is just a justification why we divide the 20 into each of the terms. Now, I could, and many of you would be comfortable just saying that 40 divided by 20 is 2. Crossing out this 20, crossing out the 40, and putting a 2 here. Now, don't divide the 20 into the 40 and the 100. Then you'd be dividing by 20 twice. The best way to do this here, to reveal the result of 222, is to divide the 20 into the 40, and of course, 40 divided by 20 is 2. But to show that even more explicitly, we can replace the 40 with 2 times 20. And each of the 40s replaced with 2 times 20. And then, because in this term it's 2 times 20 times 100, we can cancel the 20 with that 20. Now we have 2 times 100. Cancel the 20 with this 20 in the second term. Cancel the 20 here. And what do we have? 2 times 100 plus 2 times 10 plus 2 times 1, which is 222. So this is just a different way to divide 4,440 by 20. We get the same result as up there. But this shows more in a better way why it works. And one last thing. This right here, 2 times 100 plus 2 times 10 plus 2 times 1 is what's called the expansion of 222. The normal expansion of 4,440 would be 4 times 1,000 plus 4 times 100 plus 4 times 10 plus 0 ones. The expansion we had earlier was just a slight modification of that. Normally, an expansion of a number, you can only have a single digit times the power of 10. We had 40 times 100, but that's the same as the 4 times 1,000. And then we had 40 times 10, which is the 400, and we had 40 times 1, which is the 40. So it's just a slight variation on the expanded form of a whole number. So that's it. That demonstrates why it works for 479. Let's do the other one. I've done for the 289 the same thing that I did for the previous one. Showed just about all the work except for the carried digits up here. The sum of the 6 permutations, 4,218. The sum of the digits in one of the numbers is 19. And the long division algorithm here, 4,218 divided by 19 gives us the 222 again. Let me go through a little bit more quickly the expanded form, the somewhat altered expanded form of this number is actually 19 times 100, right? In each column, there are 2 2s, 2 8s, and 2 9s. Now, 1 9, 1 8, and 1 2 add up to 19. 2 of them have to add up to 38. So the digits in each column add up to 38. So in the hundreds column, we have 38 times 100 plus 38 times 10 plus, because the sum of the digits in the tens column is 38 times the 10, and the sum of the digits in the ones column, we can just put 38 or 38 times 1. Now, this is sort of an alternative expanded form of 4,218. The normal expanded form of 4,218 would be 4 times 1,000 plus 2 times 100 plus 1 times 10 plus 8. But if you evaluate this, you will get 4,100 plus 200 plus 18. I'm sorry, 4,000, not 4,100. And of course, these add up to the 4,218. With our slightly altered expanded form of the number here, what we have is 3,800 plus 380 plus 38. Again, this is not the normal expanded form of 4,218, but it's equivalent, all right? We get 8 here when we add these, 1, carry the 1, 12, carry the 1. There's the 4,218. And really, there's no surprise here. It had to be that way. This has to be 4,218 because we've got 38 hundreds, 38 tens, and 38 ones. They have to add up to the standard form of the sum, 4,218. Now, we will, of course, divide by the sum of the digits in one of the permutations, which is 19. And earlier I showed that I said 38 is 2 times 19. We cancel the 19 with the 19, be left with the 2. I won't rewrite it that way. I'll just take a little shortcut. 19 into 38 is 2. 19 into 38 here is also 2. And 19 into that 38 is 2. So once again, 200 plus 20 plus 2, there it is, 222. But we're not quite done. We're going to prove that this little social media sensation that I found always works. No matter what the 3 digits are, as long as they're all different. If they were not all different, you would not have 6 permutations. And we're going to think of the general 3-digit number with different digits as A, B, C, and the other 5 permutations. These are the 6 permutations of the letters A, B, and C. You can see 2 A's here, 2 B's here, 2 C's here. Not surprising. That's how it works. And in each column you have 2 A's, 2 B's, and 2 C's. One quick word about the symbolism here. Ordinarily, by now, you would look at something like ABC and think that means A times B times C, but not in this case. There are a few exceptions to that general rule that when 2 things are right next to each other, it's multiplication. An ordinary standard form whole number like 23 is an exception. That's not 6. That's 2 times 10 plus 3. Another exception is the so-called mixed number. That does not mean 3 times a half. It actually means 3 plus a half. And in the context, when we encounter these things, we know the context and we know not to think of that as multiplication. If we wanted to think of it as multiplication, we'd have to add some other symbol like an X or raised dot or put parentheses somewhere. So none of these being A times B times C. What they actually mean is this first one is A times 100 plus B times 10 plus C times 1 in the exact same way that we did with the other actual numbers, if you will. Well, each column has 2 A's, 2 B's, 2 C's. So how many hundreds do we have? We have 2 times A plus B plus C times 100. Okay? This is the sum of the digits. 2 times A, in parentheses, A plus B plus C, and then multiply that by 100 because that's the value of each digit, the value of each digit in the hundreds place is that many hundreds. A quick reminder about the distributive property, ladies and gentlemen. The distributive property is often stated this way, something like this: A times, in parentheses, B plus C. And it's called the distributive property because the A here gets distributed to the B and the C as a multiplication, and then we add those two products, like this. This is the distributive property, and it's extremely important in mathematics beginning all the way down in third grade. You cannot multiply numbers once you get past 9 times 9, pretty much. You can't multiply whole numbers without really the distributive property being in play. Even if you don't notice it in the standard algorithm, the distributive property is sort of hiding behind the scenes. Well, the distributive property, like many of the properties of math, could be extended to more cases. And this works exactly the way you would think it would work. It would be distribute the 2 to each of these terms, 2 times A plus 2 times B plus 2 times C. And now what's 2 times A? It's A plus A. You learn that at a very young age, that 2A is the same as A plus A. Plus 2B is B plus B, and 2C is C plus C. So there you have 2 A's, 2 B's, and 2 C's being added together. That is what this means. This is equivalent to 2 A's, 2 B's, and 2 C's being added together. So continuing here now in the middle column, we have the sum of the digits is 2 times, in parentheses, A plus B plus C, but in the middle column, that's the tens place. So we'll multiply the sum of those digits by 10, and then in the ones place, we also have the digits adding up to 2 times, in parentheses, A plus B plus C. We could put a 1 there. We don't have to, just like before. Now, the second part of this little internet curiosity is to divide this sum. This is the sum, ladies and gentlemen. I think I meant to say this at the beginning. I don't think I did. When you add up these 6 numbers and divide by the sum of the digits in one of them, you're going to get 222, even though we don't know the value of A, B, and C. This is the beauty of algebra. This is the beauty of bringing letters into mathematics to show that things work in general, to prove things. And it's really not a curiosity. It's not a magic trick that somebody's doing on the internet. It's just the nature of the mathematics forces it to come out this way. Now, the sum of the digits in one of these numbers is A plus B plus C. So we're going to divide this sum. This is indeed, what I just wrote here, is the sum of those 6 whole numbers. I'm going to divide by the sum of the digits in one of them, which is A plus B plus C. Do you see it now? You should. Even though we don't know what A plus B plus C is, in this first term up here, we have 2 times A plus B plus C times 100, so we can cancel this A plus B plus C with that one there. And of course, as we saw before, we have to do that in each term. Cancel that A plus B plus C with this one down here, and cancel that one. Maybe you didn't believe at the beginning of this particular one here, the ABC and its permutations, those 6 numbers. Maybe you didn't believe we could show that when you add the 6 and divide by the sum of the digits of one of them, you still get 222. Even there it is. 200, 2 times 100, plus 2 times 10, 20, plus 2 times 1 plus 2. There it is, the same 222. So, ladies and gentlemen, math is a very powerful tool for exploring the reality of the numbers, not just doing arithmetic operations and getting the correct answer. That's an important part of mathematics. in school in K through 12, those calculations, but mathematics is much more than just that. I'd like to, just before I close off, summarize all the things that went on in this two-part video, and I'll probably leave some out. We learned about factorial, which is a small part of some math that you will encounter in high school. N factorial is, n is a whole number, n factorial is equal to n times n minus 1 times n minus 2, and then keep going until you get all the way down to 3 times 2 times 1. Factorial, very simple concept, but can result in very big numbers. It didn't here when we had just the 3 digits. There were only 6 permutations because 3 factorial is 3 times 2 times 1, or 6. But as soon as you get up to some medium-sized numbers, like 26, the number of letters in the alphabet, 26 factorial is huge. It's a huge number. The number of ways that the letters of the alphabet can be arranged or ordered is absolutely huge. It's mind-bogglingly huge. So factorial is a sort of a deceptive little thing here. That little symbol, that exclamation mark, if the numbers get just somewhat big, the factorial can be huge. So we looked at factorial. We then learned what a permutation is. When you have a certain number of different objects, like the 3 different letters, how many ways can you order them? And it turns out to be, however many you have, it's that number factorial. That gives you the number of permutations. And in this video, part 2, where we saw why this little problem where you get 222 as your answer, why it works with the 479 and the 289 earlier, and then even generally with A, B, and C, we had to review place value, something that goes all the way back to 1st and 2nd grade. So this is a beautiful little problem. I hope that you enjoyed it as much as I did. It's not something you're going to find like this is going to be a chapter or a section in your textbook, this exact problem, but when things are presented in the textbooks, they're, you are presented with important skills and definitions and concepts in mathematics, like the distributive property. That's another thing that is reviewed here, is the distributive property. But the important thing is that you'll be able to take those and apply them, and that's what this was. This was an application of many important math concepts that you should already be comfortable with. It's going to be your responsibility going forward in classes I teach you and when you're in high school to take what you know and apply it to a situation in order to solve a problem or answer a question. And the joy and satisfaction that you get being able to do it, I hope, will outweigh any difficulties or frustrations you have going on. So that's it for now, ladies and gentlemen. I hope you enjoyed 222. Maybe if I continue using this with my students, I'll call it the 222 videos. Bye-bye.